Hello everybody, I hope you're doing well. Welcome back to another video in the probability statistics series. So today in this video, we're going to be talking more about the idea of unbiased versus biased estimators. And in particular, we're going to be talking about estimator for the population mean, right? So what did we talk about in the last video? Well, we talked about in the previous video about the idea of, sampling as a way to estimate population parameters. So we have our population here. We're going to take a sample, we're going to take another sample, and we're going to repeat that process. And from each of these samples, we get an estimate. Da, 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 da. And from that estimate, we can kind of, you know, plot the distribution of those estimates, right? And see that, the average of the estimate equaling the parameter, right, means the estimator is unbiased because the average of, these estimates would tend toward the real value of the parameter, which means that the estimator is unbiased. So what are we going to be talking about today? Well, we're going to be showing, right? So we're going to show that the sample mean is an unbiased estimator. So a bit of notation here, right? So this is the task right here. So a bit of notation. So mu is the population mean. X bar is the sample mean. And we're going to have these random variables, x1, x2, all the way to xn be the sample, right? So this guy here is the sample, right? So what do we know about the sample? So we know that the population has a mean of mu, right? And we're going to be taking samples x1, x2, all the way to x sub n, right? And what do we know about the sample? Well, when we were picking x sub 1, for example, right, we don't know the exact value of it, right? Because you're just going into the population and choosing, right? It's kind of like if you have a bucket, right? I'm taking something from the bucket. I don't know what it's going to be beforehand, but I know I'm going to collect a value, right? So this is kind of like akin to, our analogy of asking one person what was their height in the town, right? So we're going to take x sub 1, there's a value, x sub 2 will have a value, and so on to x sub n. And, calculating the sample mean, right? By definition, x bar equals the summation of I equals 1 to n of x sub I over n. And there's one other key assumption we're going to have, right? So one key assumption, right? x1, x2, all the way to xn were chosen independently, right? So this is akin to me asking, people in a fair way what was their height, right? I'm not like, saying if I choose, you know, the neighbor next door as X1, for example, to ask about their height, I'm going to ask, their children and so on and so forth necessarily, right? I'm not like, predestined to a particular path, right? I'm just choosing, say the neighbor next door and then maybe somebody in the grocery store for X2. So X sub 1 to X sub 2 all the way to X sub n are chosen independently, and this would help to mitigate bias, right? As you can see from the real world. And there's another key assumption, and we're going to assume that the expected value of x sub I equals mu. Now, why is this assumption a good assumption, right? Well, this assumption is good because we're going into this problem knowing that the population mean is a value mu. We don't know what the value of mu is, but we know that the population mean is a value, and we're going to call that value mu. So when we were asking people about their height, right, you didn't know like beforehand, right, what the height was, but maybe you could take a guess and be like, I would probably expect, Bill's height in the town to be the average of the residents, right? Because if we knew that the average height of the population in our town was mu, right? Then our expectation, right, of what we know about the height of the individual resident is limited to the fact that, their height might be the average height of the population, right? So that's why we're going to use this assumption, right? And it kind of makes sense when you think about it intuitively, right? So again, we don't know the value of x sub 1, x sub 2, x sub n, like those heights in our example, like beforehand, before we made the sample, right? But we know that the average height of the residents in the town is going to be mu. So you would be going in with the expectation that maybe the height of the resident is the average height of the town, right? So with that in mind, how do we prove that x bar right here, right, is an unbiased estimator? Well, what is the definition of an unbiased estimator in this case? Well, we have to prove that the expected value of x bar is mu. So how do we do this? Well, we know that x bar is the summation from I equals 1 to n of x sub I over n. So this will translate to the expectation of 1 over n summation I equals 1 to n of x sub I. Now we're going to use some properties of expectation. So from the previous video, right, on expectation, we know that n is a constant, right, because n is the sample size. So 1 over n is going to be constant. And we can pull constants out of expectations, right? So this is equivalent to 1 over n expectation of summation equals 1 to n of x sub I. Now, what does the summation really represent right here? Well, the summation from I equals 1 to n of x sub I is simply, you know, 1 over n expectation of x1 plus x2 plus all the way to xn, right? This is the definition of summation. And when we are having the expectation of a sum, it's the sum of the individual expectations. So you can essentially distribute the expectation over the individual terms. So this is going to be equivalent to 1 over n times expectation of x1 plus expectation of x2, so on to expectation of xn, right? And what is our assumption? Well, we assumed this assumption right here is that the expectation of x sub I is mu. So this is going to be 1 over n times mu n, right? Because you have n of these terms right here, and the expectation of these individual terms is going to be mu. So the n's here cancel out, and we're left with mu. So we have proven that this equality right here holds. So that means if we took the sample mean and calculated in this regard, right, then the average of those sample means, right, or the expected value is going to approach the population mean. So thus, this estimator is unbiased by definition. So hopefully this proof kind of makes sense to you. If you have any questions, leave it in the comments and I'll try to get to you. But thank you for tuning in. And in the next video, we're going to be talking about the estimator for the population variance.